Welcome back to Chem 4300. In this video, we're going to finish up Chapter 10 on wave-particle duality. Now, at the beginning of this chapter, we learned how light, which everyone thought was a wave, could actually be described as a particle with wave-like properties. This idea was put forth by Albert Einstein on the basis of experimental evidence from black-body radiation and from the photoelectric effect. And what Einstein worked out was that the energy of this particle, this photon, was linear proportional to the frequency of the light. So E equals h nu, where h is the Planck's constant. He also worked out the momentum of this particle was related to the wavelength that by an equation which was P equals h over lambda, where h is Planck's constant and lambda is the wavelength. Or if you like, the relationship was that the momentum vector was linearly proportional to the wave vector with Planck's constant divided by 2 pi, or what we call h bar. So we saw that in the beginning of the chapter, and that was all worked out by Einstein about 1905. Now, later, as evidence was coming in on the structure of the atom and sort of the particles were being discovered, like the electron, and models were being put forth like the Bohr model of the atom, there were some problems in trying to get all of this to work, and with the sort of classical physics approach. So it was that point that Louis de Broglie proposed this idea that if light, which everyone thought was a wave, could be a particle with wave-like properties, then perhaps particles could have wave-like properties also. So he similarly worked through this hypothesis and came up with the relationship that Einstein also found for light particles, which is that the momentum is equal to Planck's constant divided by wavelength. And indeed, for electrons moving at relatively slow speeds, you can show that electrons have the wavelength that's very similar to X-rays, and that when a beam of electrons hit a diffraction grating, such as in this case a nickel crystal, that we get constructive and destructive interference and we get a diffraction pattern. So that was the evidence that matter at the atomic level actually had wave-like behavior, even though we also could think of it as a particle, that we needed some newer type of physics to describe what was going on. So at this point, we had clear evidence that de Broglie's matter waves were real and could be measured, but we needed a wave equation. We know that if we have a wave, there should be a wave equation that governs it. And this is where Erwin Schrodinger comes in. And Schrodinger was looking at the results in terms of how the energy of this wave was related to frequency and how the momentum of the particles were involved. And he thought, can I come up with a wave equation that's consistent with all of these constraints to describe this wave moving through space? And he didn't derive it from first principles. He just tried to take the available information and put together an equation that was consistent with all that was being observed at the time. And I like this quote by Richard Feynman, who says, when Schrodinger first wrote it down, he gave a kind of derivation based on some heuristic arguments and some brilliant intuitive guesses. Some of the arguments he used were even false, but that doesn't matter. The only important thing is that the ultimate equation gives a correct description of nature, and indeed it does. So we're going to look at how he proposed this equation, and we'll look at how this equation, when you try to solve it to get the wave functions that are solutions to this equation, give you answers that are pretty much spot on with experimental results. Generally speaking, though, this is what we call the non-relativistic wave equation for quantum mechanics. Once you get into relativistic issues, then you have to abandon the Schrodinger equation and move on to something more sophisticated than that, which we won't be able to get into in this class. So let's take a look at this derivation. Well, not really derivation, but the way it was sort of proposed. So Schrodinger set about to find this equation, and he knew that these matter waves were undergoing constructive and destructive interference just like light. So he assumed there must be some kind of superposition principle at play, and so that this must be some kind of linear differential equation. He knew that he had to be consistent with these de Broglie-Einstein postulates, that the momentum is related to the wave number, or wave vector if you like, and the energy was related to frequency. he wanted to have some kind of general expression that took into account any arbitrary potential that this wave packet was moving in, as this particle wave was moving in. So he wrote down the total energy expression, and he said, okay, here's momentum squared. I know momentum is related to wave number, so through this relationship, so I'm just going to put a substitute here, momentum squared, and that gives me this. And then for energy, he knows that energy has to satisfy this relationship for the wave. And what he has here now is a nonlinear dispersion relationship for this particle wave. So he has omega as a function of k with an arbitrary value for the potential there. So next, he takes a look at a potential solution for this wave, and he writes down this complex wave function for just a simple sinusoidal wave function. And he says, okay, if I take this wave function and I take its first partial with respect to time, which just brings down minus I omega here, times the original wave function, I can rewrite it like this. And then rearrange that expression so I can write omega in terms of the wave function and its derivative. And then I will take the first and second derivative, he says, and I'll take the first derivative with respect to x, so that gives me minus I k times the original wave function, and then the second derivative gives me minus k squared times the original wave function, which we have here, which we rearrange to get just k squared is equal to this expression. Now, if you remember on the previous slide, we have omega, we have k squared, so now he has omega and k squared, so what we're going to do is take that expression, we're going to put in the results from the previous slide here, and just simply rearrange them. And that's the wave equation. That's all that he did. But what's most important about this wave equation is it actually gives the right answers. With this equation, Schrodinger was able to solve the wave equation for the hydrogen atom and get all of the correct solutions for the energies that people were observing for associated with all the transitions. So we'll come back to that later in this course. But this is the working equation for describing quantum mechanics in the sort of non-relativistic setting here. And it is not derived from any kind of first principles, so there's no medium that's being displaced, no mechanical medium in a sense that's being displaced that you could use to derive the classical wave equation. You can't do that here in this case. So this is the way he's proposed this wave function. So a couple key issues here. One is that it's the first derivative with respect to time instead of a second derivative. So remember, in the classical wave equation, it was the second derivative with respect to time and the second derivative with respect to position. The Schrodinger equation is first derivative with respect to time, although it is second derivative with respect to position. So that's a key difference from the classical wave equation. But the other interesting difference is that the wave equation involves I. It involves the square root of minus 1, which means that complex wave equations, complex solutions, are actual physical solutions to the Schrodinger equation. So in contrast to what we did with the classical wave equation, where we used complex numbers as a mathematical convenience, we knew that waves were not complex, but it made the math more compact, and it allows us to deal with phases and frequencies very easily. But we knew at the end, when we got our solutions, we only had to look at the real part of that solution, because the real part was the only thing that was actually physical. The complex wave function was just a mathematical convenience. But here, the I actually shows up in the wave equation, which means that the solutions can be complex and be physically real. I shouldn't say real. They become physical solutions, okay? So they be physically complex solutions. So, of course, we know that complex quantities cannot be measured in the lab. So all quantities that you measure in a lab are always real. So that means that this quantum wave function can't really have the same kind of physical existence as classical waves. So in other words, these quantum waves are not mechanical waves. There's not some mechanical medium that's being displaced, that's being associated with these waves. Okay. So then it leads us to this question, well, what is the physical meaning of this quantum wave function. And there are many ways in which people have tried to explain what it physically means, but we're going to stick with probably the simplest and most commonly accepted interpretation, which is something called the Copenhagen Interpretation, which was put forth by Niels Bohr and Werner Heisenberg from, in this period about 1925 to 27. And they just said, very simply, that if you take the wave function and you multiply it times its complex conjugate, then you do get a real quantity, and that real quantity is a probability. And we did something very similar in our chapter on wave mechanics, on classical wave motion. This product of the wave function with this complex conjugate is a real quantity, and that quantity is a probability. And that's it. That's the interpretation, that the wave function is nothing more than something you use to create a probability distribution, the probability of where that particle will be, which is pretty much what Einstein said when he was talking about light, and light being a particle, that the wave function, the electric field that's oscillating, when it's squared, tells us the probability of where that photon was being emitted or absorbed. That's the Copenhagen interpretation. So with that interpretation then, this product is something that you integrate between limits to tell you the probability of the particles between those two limits. And of course, any wave function that you use in this manner, this product integrated over all values has to be normalized. So we're assuming that these wave functions are normalized. If they're not, then we have to make sure mathematically that we normalize them before we use them in quantum mechanics to obtain any kind of probability. Additionally, we will only accept wave functions that are continuous. So they're finite, single-valued, and continuous functions. So we expect then our wave function is not only normalized, but the wave function and its first derivative with respect to space are finite, single-valued, and continuous functions. So that's it for this chapter. That's the end of the sort of discovery of the quantum theory as applied to the structure of the atom and molecules. And what we're going to look at next is basically applications of Erwin Schrödinger's equation and how we can start tackling more and more complex problems in quantum mechanics. We'll start simple and build up from there. But at this point, somewhere around 1927, all of the physics was worked out. The new physics was worked out for how to describe the physics at the atomic scale. And I'll end this video with this last slide here, which was taken, this picture was taken in 1927, pretty much after all of this was all worked out and the dust had settled and they knew how to proceed for studying the structure of atoms and molecules. And it wasn't going to involve, exactly the approach that people were using in the 1800s, but it was going to require some hybrid of the quantum theory with particles having wave-like properties, then on top of this sort of classical physics picture that we learned earlier in this course. So just a few sort of names are all here, and you can just sort of take a look at the picture, but a few of the people we've been talking about so far, you can see here's Einstein, here's Heisenberg here, actually, and then I think that this next to him is Wolfgang Pauli, we'll learn about later. And this is Schrodinger, and you see, actually, there was another person I wanted to point out here, which was, Max Planck right here. Okay, so we'll continue on next with Chapter 11.